Hey guys, this is Mrs. Mendy, and today we're going to talk some about the behavior of gases. And this is a picture I like. The researchers here put out these sort of like colored smoke bombs, so they could see the pattern of the air that is usually invisible that happens above an airplane wing. So I thought that was cool. Okay, so here are the variables of gases that we'll be paying attention to. Okay, so there's a lot of variation in this, and this may be more variables at a time than you are used to, but don't be nervous. They act just the same. And it doesn't matter. You'll only have to solve for one at a time. The problem will always give you like everything except one, and you'll have to figure out that one. Okay, so here we go. Some of these you know, some of these we haven't talked about yet. Okay, so there's volume. Volume, the symbol within the equations will be V. The SI unit is liter, and the SI unit symbol is capital L. Okay, this one you know. Temperature. Temperature, the symbol within the equation is T. The SI unit is Kelvin officially, but you know there may be centigrade or Celsius sometimes, and you may have to convert back and forth. But the SI unit is K. For pressure, now pressure we have not talked about before. Pressure, the symbol for it is P. The SI unit is pascals. Um, and the SI unit symbol is big P little a. And a pascal is defined as 1 Newton of force over an area of 1 square meter. Now, pressure also has a bunch of other units, um, but that almost doesn't matter, as you'll find out. Okay, so the big one that is non-SI, but it's often used as a unit of pressure because it kind of makes more sense because pascals are super small. So we often use atmospheres or ATM, but you could read it and just say 1 atmosphere equals, and look how many pascals it is. I mean, because this is a ridiculous number. And you know how scientists are lazy and they like to do the least amount of writing possible. So they're just like, yeah, if we're dealing with atmospheres, let's just make a unit for that. So 1 atmosphere is the average amount of pressure in the air on Earth at sea level. And so it's just kind of like, yeah. So sometimes we just like assume, it's like, yeah, assume that the pressure is 1 atmosphere. The pressure, of course, is always going up and down because the weather and everything. But you know, in science, sometimes the real world is too complicated, and we make simplifications. Oh, this is a thing that we will have in the classroom for you to play with, and it's called a Cartesian diver. And how do pressure and volume explain how this works? So think about this. In this thing, there's a little floaty inside. It's a dropper, and when you squeeze the bottle, the dropper goes down, and when you release the bottle, it goes back up. How does that work? I will leave you to think about that. You can talk about it in class. Okay, Boyle's law. I will never in a million years expect you to know the name of this law because who cares? That is, I mean, it's history. Bleh. Uh, you know, you could know it, but who cares? It doesn't affect how it works. Anyway, what it is that pressure and volume do the opposite of each other. Okay, and it's pressure and volume of a gas at one time is equal to the pressure and volume of the gas of another time. Now that's assuming the temperature is the same. It's assuming it's the same amount of gas, you know, in terms of moles of gas, molecules of gas. Okay. But if everything else is equal and only pressure and volume are allowed to change for gas, as the pressure goes up, the volume goes down, which makes sense, right? If you had a container of gas and you squished it, the volume would go down. Okay. As the volume goes up, the pressure goes down. Sure. Okay. So I think of this as like PV equals PV in my head. That's how I remember this equation. Again, you will not have to remember this particular equation. I'd give it to you, but you'd have to know what it meant. Okay. Oh, yeah. Calculation hint. So this works so long as the units are the same on both sides. Okay, so whatever you put in, that's what you get out on the other side. So if the pressure is in atmospheres, or the volume is in gallons, or milliliters, or cups, or whatever, so long as it's the same on both sides, you don't have to bother converting. Okay, and maybe when you take full on chemistry, your teacher will make you use a whole bunch of different pressure things, convert and stuff, because there's all kinds of like people have been measuring pressure for a long time, so there are a lot of different weird units. Okay, so think of this as a thought experiment, and we'll do it in class. So, what happens to gas volume if you heat it or cool it? Okay, so we'll be putting balloons over some flasks and heating it up or cooling it, and think about what would happen. Okay, Charles's law. Again, I'm not going to make you memorize this. I'm just telling you because that's its name. Th- and the idea of this is that temperature and volume follow each other. They go in the same direction as each other. So, like as temperature goes up, volume goes up. Which, sure, yeah, that makes sense, right? Because gases expand when you heat them. So as the temperature goes up, the volume goes up, and that's other things being equal. So that's like keeping the pressure the same and keeping the amount of gas that you have the same. As the temperature goes down, the volume goes down. Also, this is less uh, apparent if you're just thinking about it. If you change the volume, the temperature will change. So, like if you expand a gas, you make it expand, it cools down. It cools down. Okay. If you squish a gas, it heats up. Strange, but true. Okay. How your refrigerator works is by expanding a gas, and that's how it makes things cold. Okay. Anyway, so V1 over T1 equals V2 over T2. Now, tricky. This works so long as the volume units are the same on both sides, just like the PV equals PV, but the temperature has to be in Kelvin. Always convert your temperature to Kelvin. Okay, there's a mathy reason why you need this. It's because negative temperatures mess everything up. So just convert to Kelvin to be safe always. It's the SI unit. You ought to. Okay, so think about what happens to gas volume if you cool it really fast. And there will be a demonstration that goes with this in class. Okay, so think about it. What happens to gas volume if you cool it? Think about what may happen. We're going to do this in a pop can. Okay, so I've told you two equations so far, PV equals PV and V over T equals V over T. These are really part of one thing. So this is the ideal gas law, and it has pressure and volume and temperature all together, and it's a combination of those two, and it's better. It's better. Like when I think about this, you don't have to, but when I think about this, I just think about PV equals nRT, and then I derive out the other things. I'm not going to make you do that, but just know these are the same equations combined together. Okay, so new players in this, because I might make you calculate this. Um, little n, that's moles of particles. And in science in general, little n means the count of something. It's kind of cool, even in biology. So moles of particles here. And then R is just kind of a messy constant that makes the math come out right. Because it's not, these aren't perfectly together because, there's different units. How could it come out perfectly together? But they're consistently, they change together. But this constant just makes the math come out right. And I will always give you the constant. Okay. And there are different versions of it depending on which kinds of units you're using. Okay. Let's do an example problem of the type that I will make you do next. All right, so we'll do a PV equals PV1. And it's P1 equals V1 equals P2 equal times V2. Anyway, so let's say the P1 is this, V2 is this. I'm sorry, V1 is this, V2 is this. And we want to find atmospheres because that's the pressure unit that we're using. Okay? Now remember, and this is more important than ever, the first thing you do always, always, always is write the equation. Okay? Write the equation. And this is going to get confusing. If you don't try to do this in your head or just try to do it on the calculator. You are for sure going to mess it up a significant fraction of the time. Okay? Don't do it. Don't do it. All right. So here's the equation. And I would strongly, strongly recommend that you just solve for what you want. Okay? So just when it's just letters, you're going to solve for P2. Okay? Because if you've got big numbers like this, you don't want to be throwing these around on your paper so much. It's much more likely that you'll make an error. Okay, so if we're solving just with the letters, solving for P2, how do we get P2 by itself? Well, we're going to divide both sides by V2, okay? So it cancels out on this side, and so we get P1 V1 divided by V2 equals P2. All right, and then you just plug in. Okay, so let's plug in. So P1 equals this, V1 equals this, and V2 equals this. And now the work is over, really. It's just a calculator problem. Okay, so this times this divided by this on your calculator. You don't have to figure out this first and then divide by that. Your calculator can totally handle it. This times this divided by this is this. Now remember, it's not a real answer unless you have the units on it, okay? Because who knows what that is otherwise. Okay, so 5.054 atmospheres. If we were doing this in significant figures, you'd have to have 5 significant figures. Really, I'll just tell you to round it to some point because I'm not trying to kill you. Well, if I wanted you to do significant figures, I would always say round to significant figures. Okay, let's do a different example using V over T equals V over T. Okay, here's what we're doing. Here's what we've got. We've got T1 and V1 and V2, and we want T2. Okay, so we're wanting kelvins. Why did I put kelvins? It should just be Kelvin. Anyway, okay, first thing, write down the equation. Every time, I am not kidding. You do 20 problems, you're writing that equation down 20 times. Okay? That is how you get 100% on stuff. Okay. Solve for T2. Now, this one makes people nervous because it has division in it. You guys, you know algebra. You can solve for T2. All right? Here, let's do it. Okay, so solving for T2, we multiply both sides by T2. We have to do that because it's underneath. Underneath, okay? It's underneath. It's being divided by T2. We can't have that. We can't have that. All right, so we multiply both sides by T2. So we get T2 times V1 over T1, which was there before, equals V2. Okay, now we got to get rid of this other stuff and just get this by itself. All right, so first I'm going to multiply by T1. Okay, multiplying both sides by T1 gives me this on the right, this on the left. So it just gets rid of this. Okay, now remember we want T2 on the left. So now we're going to have to divide by V1 on both sides. And we get this. Okay? Okay, so T2 equals V2 times T1 divided by V1. Now, this is why you need to be careful doing this because these really matters. It really matters which one is which, V2 and V1. So be careful when you're doing this. And, always write this stuff down because it's so much easier to just look over and say, what's V2? Oh, here's V2 instead of like reading the problem or whatever. Okay, so let's plug in. Oh, before we plug in, is the temperature in Kelvin? Because remember, this equation that has T on the bottom, the T temperature has to be in Kelvin or it's going to mess up. Okay? Okay. But it is, yes. If it weren't, if it were something else, you'd have to convert, and you know how to convert temperature. So that would be fine. You just have to remember to do that step. Okay, so if we plug it in, this is what we get, 32 times this divided by this, and now it's just a calculator problem. The real science work is done. Okay, you get this giant big number, which you can round off. Okay, remember, usually I tell you to round to 2 decimal places, so that's what I did. Remember, it's in Kelvin, because that's what you put in and that's what you had to put in for this kind of problem. Okay, now you're ready to try yourself. I will see you next time.